Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 48, we will talk about stormwater drains. The different concepts that we will cover are on stormwater drains, hydraulic routing of stormwater, open channel stormwater drain design, and modified natural channels. So now that we have talked about sewer opportunities, we also know about the sewer sections. So the other thing that is left is the stormwater can be carried both via underground sewers, but it could be also carried via open channels, and that's why we also need to consider stormwater drains. Look into different designs of stormwater drains. So these are surface drains for carrying stormwater. We can use surface drains for carrying stormwater, and water flows from, in this case, from the catchment directly to the point of disposal via this kind of surface drains. And these are particularly these are surface drains, but it could be both open or it could be both covered. And these are of course given some gradient, so the water flows from the catchment to that particular disposal point. And usually we can say that there are three kinds of drains: primary drains, secondary drains, tertiary drains. So as you understand, tertiary drains collect water from the sub-catchments and convey it to the secondary drains. Secondary drains collect water from the tertiary drains and convey it to the primary drains. And finally, primary drains collect stormwater from the secondary drains and convey it to the disposal point. Similar to trunk sewers, intercepting sewers, then there are branch sewers, lateral sewers, and those same way we also, when there are surface drains, we also have tertiary drains, secondary drains, and primary drains. So open channels for stormwater drains, this could be either natural streams or canals that are already present in that area, which you may not need to modify even, so that becomes a modified natural channel, or it may be unmodified as well, or there could be engineered channels as well. That means you design the profile of that particular open drain or that open channel. So engineered channels are constructed to protect the natural environment of the city and the natural stream and waterways, and these are designed to form of a network of tertiary, secondary, primary drains and resemble the profile of the natural drainage system. So that means we usually follow, as we have learned that using digital elevation models and so on, we can determine that which are the actually points where the water flows from the different direction, and then based on those 4 points we can determine that okay, these are the streams that are formed, and then these streams could be identified in a particular in a particular area based on the contours and based on the digital elevation model. And then using that we can also design our artificial or engineered channels along the same those stream profiles, and then create our stormwater drains. So we can follow those basic system where we can either use the natural stream if those are there, and we can either modify them or we can keep it as it is, or we can create engineered channels for those particular streams, and we give it a profile as per the volume of water and so on that has to be carried. So stormwater channels, particularly secondary and tertiary drains, which are smaller ones, and this you will find in an urban area, and these are channels which could be made of brick or it could be made of concrete, but usually these are covered with RCC slabs, so that in most drains in today's context we make them covered, so that there is no point there, so that it is covered, so that there is no dumping of solid waste, there is no spillage of the roadside dust and other material into the drain, and also to prevent unhygienic conditions or aesthetics, to maintain aesthetics. So all these reasons we usually use slabs to cover the drains. And the RCC slabs are usually of smaller lengths, and there is a precast, and usually they are designed so that 1 or 2 persons can actually lift it with using hooks or so on, so that they can lift it, remove it, clean the drain if required, and then again put it back. And slabs are placed over the drain and joined with cement plasters. For some other sections where it doesn't need to be lifted, we can actually plaster it with the existing drain profile made of bricks or made of RCC. And then sometimes the slabs are removed, the slabs which could be lifted, those are removed, and then the drain needs to be cleaned at certain intervals. For larger drain sections like secondary and primary drains, and usually we can think of, like in this particular case, because it takes up quite a bit of area, particularly in the urban area, we can think of covering them, and we can extend, if we cover them, usually these drainage channels go along the roadways and all, and along the road network. So you will find the canal going along the road network, which is primarily a canal for this stormwater drainage, and there we can actually create covers on that particular canal or extend the right of way of that particular road, and that we can use that particular space as well. And if it is not so, in that case at least we have to fence it or put a small parapet, so that accidents are not happen, like people fall over or vehicles fall over and so on. So sometimes we also use RCC box drains. That means instead of just the cover, the entire drain is made of RCC, and these are provided in case we don't have space and we have heavy vehicular traffic, and street inlets are provided between 15 to 30 meter interval. That means those are inlet points through which water can enter into these stormwater drains, and these are laid 200 to 300 mm below ground level at suitable gradient, and access holes at intervals of 30 meter for cleaning. So that is how this box profile drains are a little bit below ground. The traffic actually flows over it, and at certain intervals we give openings so that those sections could be taken up and we can do the cleaning. And we also provide inlet so that water can enter into these particular drains from the road surface or from the surroundings maybe, and that is also at 15 to 30 meter interval. For flyovers also needs to be drained, and the rainwater that accumulates over a flyover has to be taken down, as you can see, via pipes which are embedded in the piers, like you can see that goes along the piers, and this is how the water comes down from the flyover. So this is the inlet point from the flyover, and the water comes down, and along these pipes we take it via that. So there are no straight drops. That means directly the water doesn't falls down, it is taken to a point, and along the piers we take them down, so that there is provision of drainage over here. And minimum pipe sizes are used as 100 mm, and that is how we drain the flyover. But not all water comes via the inlet. Some water flows over the flyover and goes towards the bottom of the flyover. So usually flyovers are has a longitudinal slope. That means flyovers definitely is like this. So there is a longitudinal slope. So water will flow along the longitudinal slope, and this gradient is around 3%. Plus there is sometimes a cross slope also given, which is around 2%. So the water not only goes down but also goes towards the side, because a cross slope of 2% is also given. So a huge quantity of water reaches the ground over here. So usually we see if a lot of water comes down from the flyover, and usually there is a ponding at the bottom of the flyover. So this needs to be taken care of. How we do that? So usually we put a finger plate drain across the pavement. So at the bottom of the flyover we put a drain over here. It's a finger plate drain. That means there is grating over the top of it, so that water, while coming down the flyover, it is trapped by this drain and the water goes down. And from here it is either it is this downstream road pavement also slopes to the so down. So we have the flyover, then the road is like this. So we have this finger drain over here. So water from both the downstream side and from the flyover side both comes to this point. So that means the downstream road pavement, this also slopes towards this particular valley curve area at this particular point. That is why if this drain is blocked, we will see ponding over here. But this drain needs to be make sure that designed following the runoff rational formula. From there we can estimate the amount of runoff, and as per the design in rainfall intensity we can design the size of this particular drain. And if the connecting drainage system is not adequate, we have to make sure that this water is pumped out of this particular drain and put it into the sewer channel, a sewer network, or into a open channel, whatever the case may be. So, similar to flyovers, and this is that this finger drain that we are talking about, and this similar to flyovers, for subways also we need to consider drainage, and surface drains of subways taken to the lowest level and a grating is provided. So, subways, of course, the road goes down, so the water comes to the bottom. So, there again grating is provided and we collect the water in this particular drain. And across the, and this grating is provided across the full width of the road, and this disposal chamber below collects the storm water and disposal via gravity or pumping to stormwater drain. So, this, because it is at a low level, it may have to be pumped to a stormwater drain, but if the stormwater drain it has a lower level, then directly it can connect to that. And sometimes 2 inlets are provided for larger subways. So, that is as per requirement, we will provide the number of inlets. Now, now that we have talked about stormwater open channels and drains, we also need to talk a little bit about the hydraulic routing of stormwater, because hydraulic routing of stormwater is different from the flow of water in closed conduits. Now, usually in case of stormwater, the catchments, as we know, that receives rainfall and they generate runoff, and this runoff is actually can be shown as an outflow hydrograph. So, we have discussed about unit hydrograph, and we can combine multiple unit hydrographs into a hydrograph for a particular channel section. So, this runoff for a particular area can be shown as a hydrograph, and hydraulic routing actually predicts the shape of the hydrograph as water moves through a channel or a reservoir. So, that means this hydraulic routing is actually the prediction of how much what amount of water will come to this particular point which we are considering, and then based on that, what would be the hydrograph. That means the cumulative amount of water that comes to that particular point over time. So, this helps in forecasting of the design of spillways. Spillways are water channels through which stormwater is taken out, reservoirs, and flood protection works. So, sometimes we give detention basins, retention basins. So, reservoirs has to be designed, and other flood protection works has to be designed based on the amount of water that is being forecasted to come. So, this is also called flood forecasting, because this water flows on the overland surface and then it comes. So, it may create flood if it is not drained properly. So, that is why we also call it flood forecasting. So, stormwater flows through channels and conduits in unsteady conditions. Till now, when we have discussed earlier, we have discussed about steady flow conditions. That means, in a particular channel, the total volume of water, that means the height of water in that channel, more or less remains same. So, there is no change in that. But unsteady flow means there is turbulence at the top of the water, right. So, the height of water also changes at certain points. So, this is called unsteady condition. Flow rate, velocity and depth vary in space and time throughout the channel and conduit. So, that is why it is called an unsteady flow. So, because the height changes, flow rate changes, velocity also changes. So, these are the problems, these are the conditions that we have to deal with stormwater. And the other thing is, I will talk about that later on. Let me go through it. Unsteady flow analysis. Flow and elevation of water surface both are unknown, and this needs to be solved. So, that means previously we were only solving the flow of the water. That means the total volume of water along a channel was same in the different sections, and accordingly we were solving the profile of that particular section that is required. But now the elevation of water surface is also unknown. That means the elevation of that water, that means depth of flow would be also different at different parts of the section. So, earlier we were considering in a particular sewer section the depth of flow like half full or maybe 2/3 full or 1/3 full. So, we are considering a particular fixed depth of flow, but now it is not fixed. So, that is the difference from steady state flow. So, when we solve this kind of problem in the previous one, that means we talked about conservation of water mass. So, that means it is also called a continuity equation. That means in between two sections when water passes from one to another. So, when we consider continuity, then we consider conservation of water mass. That means the total in steady state flow, it is same and the elevations were not considered. That means, if we know the elevations, that means the total volume of water was more or less same, that is passing through. But now, because there is unsteady flow, we also need to consider the conservation of water momentum. That is, along with conservation of mass, we also need to understand that water momentum, the total energy that goes into that, that also is conserved, right. So, water momentum is also conserved. So, that means the equations that we need to solve is not only for conservation of mass, but also for conservation of momentum. So, that is what is different in case of stormwater flow. So, now I am going a little bit into the advanced hydrology part. So, just have a basic idea about this systems, so that when you come across this, when you use the softwares, that you will find that in the software they will ask you, are you going to use kinematic wave for this routing, or diffusion wave, or dynamic wave, because all of them will give you the same results, right. But you need to understand where to use what and why this, what are these terms all about, right. So, that is why we need to get into a little bit about into the details of this advanced hydraulics. So, there are so as we said that we have to maintain both conservation of mass, we have to follow conservation of mass as well as momentum. So, we use partial differential equations known as Saint-Venant's equation. There is another set of equations called Navier-Stokes equation, but anyway, so if you know this, that is adequate. That is Saint-Venant's equation for one dimensional flow. So, one dimensional flow refers to whenever this water is flowing along a storm channel, it is flowing in one dimension, but if it is flowing in multiple directions, then we can call it a two-dimensional flow, right. So, we are usually concerned with one-dimensional flow, but when the water flow inside a channel, but when the water is flowing along the surface, usually the water flows in multiple directions, right. Or like for example, there is a dike, the water gets obstructed by the dike, then it will once it will climb over the dike, or the level reaches up the dike, then it will flow in all directions, right. So, that is a two-dimensional flow, right. So, the flow of water over a land could be either one-dimensional or two-dimensional, but usually we will talk about one-dimensional flow. But when we will model the storm flood modeling, then we will consider two-dimensional flow as well. That I will show you in the final module. So, in this partial differential equation known as Saint-Venant equations, this can be applied to solve this conservation of momentum and conservation of mass together, and that but for one-dimensional flow along these stormwater channels. And when we solve these equations, we can actually get the flow rate, the velocity, the depth, all these things could be solved from that one. So, there are three ways we can solve it. One is the kinematic wave. This is the basic hydraulic equation that includes both gravity and frictional forces balancing each other. Other terms are neglected. So, this is primarily we are maintaining that we are considering that only gravity is acting upon the flow and the frictional forces, because it is flowing through a water channel. So, usually in steep channels that is the case, that means where the walls are very steep, this stormwater flows through that, then we can ignore the other forces, only the gravitational forces and the frictional forces are considered. But we can also have diffusion wave routing equations, or which actually incorporates the pressure term in addition to gravity and frictional forces. So, in addition to gravity and frictional forces, we also consider the pressure in that water. Then finally, the dynamic wave equation considers all the terms of the momentum equation, where the movement of water is also considered and the total momentum is also considered. So, these are the three sets of equations that are used. To give you a little bit more details, as you can see that in kinematic wave motion, inertial and pressure forces have negligible effects. So, inertial forces and pressure forces are not considered. Inertia is momentum and pressure, these are not considered. Only we consider the continuity equation and Manning's equation. These are combined together to simulate and compute the runoff of the watershed. So, in this particular equation, this is dyo by dt plus dqo dx equal to I minus f, where I minus f is rate of excess rainfall, that is rainfall minus infiltration. Whatever rainfall is left after infiltration, that is I minus f. So, this is the actual volume of water that we are considering, and this is actually we can say that the water that will flow in the channel is basically this amount of water, and that we can solve by saying that dyo by dt, yo is the mean depth of flow, and this is as per time. So, time for per each time period, we break the entire time period into smaller times periods, and we can say that for each time period what is the depth, and then qo is basically the variable flow per unit width of overland flow plane, and dx is the spatial coordinate, that means at what area we are actually determining this variable flow per unit width. So, that means we are considering both flow as well as the height of that particular this yo is basically the depth of the outflow. So, that mean depth of the outflow. So, that is why depth of the channel is required, the total quantity is required, then we can solve this using we can replace qo by the Manning's equation, and then we can solve this. So, qo becomes mu 0 into y 0 to the power m 0. So, what are these values? Y 0 is the mean depth of outflow. Sorry, this earlier this q 0 is a variable flow per unit with the overland flow, and this y 0 we already discussed. This is the depth. So, in Manning's equation we already have the depth of the flow multiplied by the slope of the flow divided by Manning's roughness coefficient and so on. So, this mu 0 is actually 1 by n, which is Manning's roughness coefficient, divided into S 0 into 0.5. What is S 0? S 0 is the average slope of the overland flow. So, you see this is basically the format of the Manning's equation, which could be put over there. So, we now have y 0 and over here we can replace this over here and we can solve this, and when we can solve this equation, we can actually get values of, like y 0 has to be solved to establish a relationship in terms of x, t and excess rainfall depth. So, what is the excess rainfall which creates infiltration? Based on that, the t and x the relationship between x and t, time and that area, all these things could be related, and when we solve this equation. So, this can be solved using analytical methods, computational methods and finite elements method. So, we have discussed this earlier, that when we were solving for a particular complex loop network, we told you that there is different methods, Newton-Raphson method and so on, finite elements method. So, this is how we solve this sort of equations. So, two things, overland flow is taken to be the flow per unit width of the plane over which we are considering it, and lateral flow is considered equal to the difference between rates of rainfall and infiltration. So, that is what we need to solve, and this is the solution of the kinematic wave, but this is the equation that we need to solve to get the values of qo, yo, x, t and so on. And in case of the diffusion wave as well as dynamic wave, as you know that in diffusion wave we incorporate the pressure term, in dynamic wave we use all the other terms of inertia or momentum. So, here you can see two forms of that, one is the conservation form and non-conservation form. So, the first equation dq by dx and dA by dt equal to 0, this is basically the continuity equation, the conservation of mass that we just discussed earlier, and then non-conservation form is where velocity is also considered. So, this velocity comes in, this is the same way of writing it, but just by incorporating velocity. The other is the momentum equation. When we consider momentum, we consider this pressure force term, the acceleration terms, both local acceleration as well as convective acceleration. So, these two terms are coming in, which are for inertia, and this gravity force term, this is S 0, and friction force term, these are also considered. So, as you know that the standard friction force and the gravity, these are there. When we add pressure, that is kinematic wave. When we add pressure, then it is diffusion wave, and when we add all of them, that is dynamic wave. So, if we solve the entire equation, then it is solving dynamic wave. If we are solving only the pressure term, then it is diffusion wave, or when we are solving just for gravity and friction, that is kinematic wave. So, these are the different equations that get solved, and usually we are like S 0 is the bed slope and SF is the friction slope, and A is the area of flow of the channel and Q is the discharge of the channel for this particular equations. But what we need to understand is we need to generate hydrographs for rainfall runoff simulation and that means for every rainfall event, runoff is generated, and this runoff is routed through channels and conduits to the points where it to the points of outfall, and we need to generate hydrographs for that. And the purpose of all this equation is to generate these hydrographs, and based on that we have to size the channels. That means based on the hydrographs of the quantity of water, we determine what should be the channel sizes and what would be the resulting computations for flow rate, velocity, depth for any of this section of this channel. So, if we know the hydrograph at each of these sections, we can determine what is the flow depth, what is the velocity, what is the total the flow rate and the depth along that particular, all these things could be solved. And if the depth varies at different distances and all, it's unsteady flow, and for that we have to use the other equations like kinematic wave, or we have to use this momentum conservation equations, where we use dynamic wave for this particular case. So, stormwater management model SWMM, I've already demonstrated that. So, it has got options where you can choose that we will use dynamic wave or kinematic wave for solving this sort of stormwater drainage channel to solve the section to determine the sections for drainage channels and so on. So, let us see open channel stormwater drain designs. There are certain considerations for them. For example, the design flow is designed for 25 years return period. So, 25 years is the return period for design of this kind of structures. The flow regime, which is determined by the Freud number, is lesser than 0.8. This actually determines the kind of flow along this particular channel. So, this includes many parameters, which includes the wave profile along that particular channel and so on. So, Freud number is important. And then design velocity with grass lining and with other linings such as riprap and concrete, this is given. So, 1.2 meters, 1.8 meters and 3 meters. So, you can see that with normal lining like grasses, it is 1.2 meter. For riprap, like where we put stones and all, then it is 1.8 meter, and for concrete we can have even 3 meter per second as drainage velocity. Longitudinal slope is given is around 0.4%, or if it's for natural lining, and for artificial, it would be more for artificial and less for natural. And for steep slope, drop structures may be provided. I will show you how to design drop structures. And for curvature into the channel, the center line of curvature should have minimum radius 2 times into top width, but not less than 30 meter. So, that means the curves that you can provide in this channel, like you can see, this is not a straight channel, it goes like this. So, the curves could be have a minimum radius of 2 times the top of the width, but not less than 30 meters. So, what is riprap? It is basically usually granite or other crushed stone. This kind of rocks are usually of size 6 inch to 12 inch, which are preferably flat, are organized at the banks to stabilize the slope and prevent erosion. So, we have already learned some amount of stabilization of in the earlier lectures of the outfall structures and all, but similarly in this kind of storm channels, we can actually line this kind of stone all along the banks, or we can make it via concrete as well. And we also need to provide certain amount of freeboard in these open channels, the open area at the top, and if the discharge is below 3 meter cube per second, freeboard is 450. If it is 300 and above but below 3000, then it is 1200, and above 3000 meter cube per second, then 1500 is the freeboard. Now, as we are saying that the stormwater channels cannot, it's not like it will go in a straight line, sometime it can bend. That means we have to provide some radius to it, and because these are open channels and water flows along that, and it is flowing along in a particular velocity, wherever there is a turn, there is a tendency to water in this particular section. Probably you will see that the water will become like this, because it is passing with a velocity because of the super elevation, and this side the water would raise higher, this side it would be lower. So, this needs to be considered in the design of the profile of the stormwater channel, which was earlier not considered in case of drainage design. So, this because the quantity of water is high, the drainage is given a slope, there is velocity, and we need to consider this super elevation. and super elevation is provided on the outside bend of the channel. So, on this side, for this case, for in this profile it would be provided on this side. So, this would be super elevation on this side, and this is you usually use this simple formula where delta y is equal to v square t by divided by 2 g into RC, where delta y is the difference in water surface elevation inside versus outside the curve, this delta y. So, this is the level inside the curve and this is the level outside the curve. So, difference between that, and v is the mean velocity of this channel, and we are trying to determine delta v because based on that we have to determine the height of this particular side of the channel, and then again we have to give freeboard. So, totally freeboard plus this height and also the height of the other side. So, together we can actually determine the profile of section of this particular channel. G is acceleration due to gravity and RC is the radius of curvature of this particular channel. So, using these 4 parameters, we can actually compute the height of the channel that has to be provided or provided for super elevation. So, this was the drop drop structures that we were talking about earlier, that when natural channels has to be stabilized to carry storm water runoff in urban areas, we need to modify them, and this drop structures are part of this modification. Modifications could be different kinds. That means we can have riprap at the side, we can have concreting of the beds, but at the same time this dropping using design of these drop structures are also part of this modifying the natural channels. And so, in addition to lining up banks and the bed, if the banks are erodible, then we design this channels and overbank capacity for 25-year return period, and we design velocity of this kind of channel is less than 2 meter per second or according to the critical velocity of the section. Manning's roughness coefficient is used for stabilized earthen channels. So, Manning's equation could be used to design these open channel flows that we have discussed earlier, and we can use stabilized earthen channel Manning's coefficient. This you can see from the coefficient table that we have also provided earlier. And so, water surface limits, like in case there is lot of drop, the slope is too high, then we can actually reduce that particular drop. So, how we can do that? For that we can do drop structures to limit flow velocities and control the water surface profile, so that it matches the hydraulic gradient as much as possible. So, this is how it is done. So, this is the vertical drop that we are doing, and you can see in the structure wise this is how we are doing that. We are modifying the channel so that the water some amount of impounding happens at certain levels. So, water falls down, then otherwise the velocity generated would be too high. If it was a uniform slope, the velocity would gradually become higher, but if it is falls like that, the velocity is controlled and erosion does not happen. So, that is why it falls from one level to another and gradually moves on. And this is another structure, which is an artificial structure which can be used, which could be looked at as a drop structure. So, we can this concrete structure which could be cast in situ, or as well as this could be prefabricated structure which could be also provided where there is a drop from one level of the channel to another level. Wherever there are significant drops, we can provide this kind of structures. So, channel linings could be both rigid and flexible, and as you these are provided for stabilizing the banks. So, rigid linings are made of concrete, precast concrete slabs, stone masonry, cellular reinforced concrete paving with infill soil, and flexible could be riprap, gravels, and gabion or random rubble. So, these are the different kinds of flexible lining and rigid lining used, and the shape of the channel is also important. Usually less the surface area, less is the lining cost, and more is the hydraulic capacity. So, the width of the channel has to be reduced as much as possible, because that will reduce the lining cost as well as the hydraulic and increase the hydraulic capacity of that channel. And semicircular section is preferred. As you know, the circular section is the best for best hydraulic capacity. So, similarly, because we are doing open channels, the semicircular section is the next best one in this particular case. So, maximum hydraulic capacity with minimum surface area in case of semicircular sections. But usually we go for trapezoidal sections. We adopt this mostly due to low cost and ease of construction and almost similar to semicircular shape. Now, why trapezoidal section? Because here we have to maintain these curves and all, but in case of trapezoidal sections we can go for like this or we can go like this. So, here it is easy to excavate and we do not need to exactly follow this kind of rounded curves. So, it is constructed relatively easier and we can actually do it at a lower cost as well. And the construction is much easier compared to the semicircular section. So, to conclude, stormwater flow through channels and conduits in unsteady conditions, thus both flow and the elevation of water surface needs to be solved. Partial differential equations known as Sen-Venance equation for one-dimensional flow can be applied to solve the above, and stormwater management model SWMM can be used for computations for all these different Sen-Venance equations. So, these are some of the references you can follow. Thank you.